In-class activity 12B, building polynomial models. Ocean tides rise and fall vertically because of the gravitational pull from our moon and sun. We refer to the rise as high tide and the fall as low tide. In most parts of the world, the oceans rise and fall twice each day. On the axes below, sketch the possible rise and fall of the waves. Let the x-axis represent the hours in a day and the y-axis represent the tidal heights. The zero tide level on the graph is the set baseline from which all other tides are measured. So why don't we start at 0 right on the x-axis there, and we're gonna go up for high tide. Let's see. And then down again, back to the baseline, and then low tide. Go down and then back up to the baseline, and that's half of the day. And let's do this again, up to high tide and back to the baseline, and then low tide. Let me make that a little bit rounder here at the bottom. And okay. There we go. Back to 24 hours. Objectives for the activity. You will understand polynomials can be used to model quantities that vary over time. The graph and factored form of the equation are related. You will be able to construct a formula for a polynomial given a list of roots. Use scaling to fit a polynomial to a graph. 2, the ocean's waves flow toward and away from the coast each day. The Pacific and Atlantic coastlines of the United States follow a semi-diurnal tidal cycle. This cycle consists of 2 nearly equal high tides and 2 nearly equal low tides. The graph below is modeling the cycle over a single day. Because the second low tide is happening at the ends of the graph, we will not be considering them in our model. Part A, how many turning points does the graph contain, and what does that tell you about the function modeling the graph? Well, for turning points, remember, here's a turning point, goes from up to down, and then down to up. And let me rescale that. Oops. Sorry about that. And then once more, we go from up to down again. So it looks like we have 3. So I'm going to put 3 turning points. Oops, there we go. So since we have 3 turning points, that looks like this is going to be a 4th power equation, or we would call that a quartic. There we go. Part B, identify the horizontal intercepts for the graphed function. Each of these intercepts represents an hour in the day, h, when the tide is at the baseline, or 0 feet. So let's see, I'm just going to go here and put little blue circles on these intercepts where the curve crosses the horizontal axis, and make note of these. I'm going to say h is equal to, well, the first one is 1. Then we have h is equal to 9. H is equal to 14. And h is equal to 23. There we go. For part C, it says express each of your horizontal intercepts as roots of a polynomial and find a formula for a polynomial function f of h with roots at all of these h values. Write your function in factored form. Okay, so our answer could be written this way. We know it's going to be f of h, and that's equal to, we know the root, if the root is 1, then the corresponding factor is going to be, linear factor would be h minus 1. Similarly, we'd have h minus 9, and then h minus 14, and finally h minus 23. And we can see this is going to be a quartic. For part D, using a graphing calculator or app, graph the polynomial function from part C. You will need to set your graphing window so that the domain, meaning the h values, go from 0 to 24. And the range, the F values go from negative 3,800 to 800 feet. Compare the graph on your calculator or app to the graph provided above. Explain how your graph is the same and how it's different from the original graph. So let's do this. I'm going to go close this and go to a calculator app here. Looks like a TI-83 or 84, and the Y equals screen. And under the Y1 row, let's enter in. I'm going to put parentheses, and we don't have an H, but we do have an X. We'll use the X for the calculator. Let you see what's going on. There's our first linear factor, and then we'll do X minus 9 to represent H minus 9, and then X minus 14, and then finally X minus 23. And it's going to hit graph. It's a standard viewing window, but it goes from negative 10 to 10 on the X and the Y axes, and that's not what we want. So let's go back and adjust our window. So I go second window, and it tells us we want to go 0 to 24. So I'll go X min 0, 24, 0. The max would be 24. The scale can stay at 1, I suppose. If not, we'll come back and adjust it. The Y values of the vertical axis is going to go from negative 3,800, wow, up to 800. Okay, let's just graph it and see what we get. Oh, there we go. That's better. And with this app, we can actually even, manipulate it a little bit without going back to the the table screen or the window screen. So there we go. We see that the intercepts, the horizontal intercepts, are at 1, 9, 14, and 23. That's what we expected. And yeah, there's how many turning points? There's 1, 2, 3 turning points. So that looks good. One thing that I noticed, it's upside down from our original graph. And I'm going to go back to the original graph here. Let me get out of the calculator app for a second and back to here. See, we have like 2 maximums and then 1 minimum in the center. If I go back to the calculator, it looks like it's just sort of the opposite. We have 2 mins on the ends and a max in the middle. So we can adjust this. I'm sure we're going to be asked to do that soon. And that is actually part E. So I'm going to go from part D back to here, and let's go to, oh, it does say in part D, before we go on, it says explain how your graph is the same and how it's different from the original graph. So why don't we do this? Because we notice that the horizontal intercepts are the same, so we could say that. We could say that the horizontal intercepts are the same. We'll put on both graphs. And then we also said that the turning points are the same. Each graph has 3 turning points. So there we go. But we did notice one graph looks upside down to the other. Or we could say the waves on the graph are opposite. Yeah. So let's say, we'll just put this here, the first thing I mentioned. The waves on these, that's not spelled correctly. How about these graphs? Opposite. And that's a good point. So why don't we go on to part E? We have some similarities and some things that aren't similar, but let's go to part E. Part E says, since the waves of our polynomial in part B are mirroring the behavior of the original graph, that is, they are behaving in an opposite manner, we need to flip the graph over the horizontal axis. Adjust your function by flipping it over the horizontal axis and then graph the new function to confirm its behavior has changed. Write your new function below. So it looks like, let me just scroll back. And look at this. Our, you know, I'm going to erase this, but looks like we had a graph that, kind of did something like this. But when we graphed it, it looked like, like that. So it looks like we want to rotate one of these graphs around the horizontal axis, kind of flip it over. So they are the same. So let me go and get rid of that I just scribbled on there. I'm going to go back to let me go back here to the calculator. And that's what we have. I'm going to make it a little bit smaller, a little bit more manageable. And we have two minimums and one max in the middle, relative max and mins there. So why don't we go back to our y equals screen and second insert. And I'm going to put a negative sign there. And it looks like our calculator wants a number also or something. So we'll put a -1. So that's good. And let's graph this. This should do what we want. And where did it go? Graph. Okay, and there's the y1 row. We enter the equation in, and then let's graph this. And it does look like we wanted. We have two ends that are higher and the middle is lower, and that is what we wanted. So by adding a negative sign in front of this, or we put a -1 actually in front of this, that seemed to work. Let me go back to part E. And it says, since the waves of our polynomial in part B are mirroring the behavior of the original graph, that is, they're behaving in an opposite manner, we need to flip the graph over the horizontal axis, which we did. And we adjusted the function and write the new function below. I'm just going to copy what we entered in under the y equals screen. So it would be f of h. I mean, we used x, f of x in the calculator. But here we're going to use the h. So -1 times h minus 1 times h minus 9 times h minus 14 finally times h. It's an h minus, it was 23. There we go. Part F. The height of the waves from the function in part E are still significantly higher or lower than the original function. Recall from preview activity 12b that to increase or decrease the height of the waves, we must multiply the function by a scale factor. Adjust your function in part E by multiplying by a scale factor. This may take several attempts before you find an appropriate value. We could go in, I'm just going to go back to the calculator and go to the y equals screen. And then I'm going to go back up here. And we have the scalar we have here is a -1. And it looks like it's too big. So I'm going to take a number less than a -1 and see if it's something that we want. Why don't we do like, how about 0.5? And second insert, I lost a parenthesis. There we go. And let me graph this and see what we have. Okay, it worked a little bit, but we're still way up. That second relative max is close to 2,000, and that's much higher than we want. So I'm going to go back in. This is just trial and error for right now. And instead of the 0.5, how about we do a insert, we'll put a 2.5 here. So down to -1/4. Okay, so we're getting closer and closer with this. We still have to, let me adjust this, adjust the screen here. And keep going. Y equals, and I was able to work with this a little bit before in preparation for this, and I found a number that was pretty small. It was 0.0, and then let me do whoops. Oops. I'm really not moving around here too well. Okay, this should be that. This should be close. So let's see what this is. We graph this, and it looks, whoa. Let me adjust the window. And that is not looking like I want. 1 second, let's check this. Okay, let's go back to the window and adjust the window. If we try X min at -3, the max at 26, and then Y min will be -3, and we'll go up to 5. This should be a better viewing window for us. So let's just graph this and see what we come up with. There we go. And I'll just scroll this up a little bit. That looks a lot better. So that's the function, or pretty close to the function that we're trying to come up with. All right, so let me go back to writing here. For part 3, why don't we write this down? So this is going to be f of h equals -0.0005, and then we have h minus 1, h minus 9, h minus 14, h minus 23. Now let's go to part 3. It says use the method from question 2 to find an initial formula for a polynomial function that matches the graph shown here. Flip the graph if necessary, but do not adjust your formula using a scale factor. All right, so what we could do, let's look at, first thing I'm noticing, let's look at the intercepts. We have x equals -2. I have x equals +4, and that would be x equals 7. So let's go ahead and write this function. I'll just use f of x is equal to, since it says x minus 2, we're going to have x plus 2 as our first linear factor, and then we have x minus 4, and then our last factor here, x minus 7. All right. So let's go ahead and graph this. Back here, y equals, and I'm going to just turn that one off and just enter this in again. So why don't we write, we'll use x plus 2, and then we have x minus 4, and then x minus 7. I'm going to graph, and then from here, I'm just going to go in and put the standard window back and see what we have. And it looks pretty large here. So our intercepts look good. They're at -2, 4, and 7, but definitely, whoops. Let me just, there we go. Yeah, our relative max here is going up to almost 60, and we're going almost, down to -20. So it said, do not adjust with a scaling formula, a factor yet. So, all right, so there's our first part of 3. And we don't have to flip the graph, so that's good. Let me just scroll down here. And it says in question 2, this is number 4. In question 2, we adjusted our function for the height of the waves simply by trial and error. This worked, but was very time consuming. Instead, we will now use the local maxima and minima to help us find the scale factor by which the function should be multiplied. This is nice. It'll make this a lot more direct, this scalar factor. Part A, state the local maximum and local minimum values in the graph from question 3. So if I go back to the graph, where are we here? Oh, it's from not our graph, the graph in question 3. Sorry about that. So it looks here. We're going to call that not quite 6, 5 something. Why don't we do 5? We'll do 0.7. And then the minimum value right there. Why don't we do negative, well, it's more than 1, not quite -2, about 1.7. Okay. And I'm going to scroll back. It says state the local maximum. Okay, so I'm going to put local. max at 5.7, local min at negative 1.7. Part B, what is the vertical difference between the local maximum and the local minimums for the graph in question 3? So if we're just going to add these together, the absolute value of these numbers. And this ends up being 7.4. Part C, using a graphing calculator or app, graph the function you wrote for question 3. What are the local maximum and minimum values for your function? So we have to go back to our graph. We already graphed this. So we go back here and it's going to get a maximum value here. It looks like, well, 57. We'll use 57 there. And then we're going to take this all the way down to the min. And that's going to be negative 17. All right, so let's go back here where we were. Part C says using a graphing calculator, graph the function you wrote for the question 3. The local max, it was 57. Well, that's what we're using. Local min was negative 17. Okay. Part D, what's the vertical difference between the local maximum and local minimum for the function? We're just adding these together again, and we're just considering the absolute value of these functions. So this is going to give us 74. Part E, find the appropriate scale factor by writing the ratio of the vertical distance of the original graph to the vertical distance of the graph from part D. So we're just going to write a fraction. It's going to be 7.4 over 74. And when we do this, we get 0.1 or 1/10. Now, part 5, rewrite the function by substituting the scale factor from part E into the equation from question 3. Graph your new equation. How does this compare to the original? Okay, so let's go back to the graph. And we're going to say done for right now. Y equals, second insert, 0.1. Let's graph this. All right, so if we this graph looks a lot like the original. So by the original, I'm going to go back to a picture that we had here, and it looks a lot like that. So the max is 5.7, min is negative 1.7. Let's just check that out. 5.7 roughly, and then roughly negative 1.7. So this looks good. Let me go ahead and write this down. I'm going to go back here. And for part 5, we're going to write f of x is equal to, the scaling factor was 0.1, and then our factor is x plus 2, x minus 4, and then x minus 7. Okay. And that is the end of this video. Thanks.